Let's take a look at fluids. Fluids are liquids and gases. They take the shape of the container they are placed in, unlike solids that keep their shape. There are a few things that we have to define about fluids. One of them is a density. That density doesn't just count for fluids, it's also true for solids. But density in general is the ratio of substance's mass to its volume. So density has the symbol rho, and rho is mass over volume. The SI units for density are the kilogram per cubic meter, but some convenient units are also the gram per cubic centimeter or the gram per milliliter. So here you'll notice that 1 cubic centimeter is equivalent to 1 milliliter. And the reason for this convenient unit is that the density of water at 1 atmosphere and 4 degrees Celsius is 1 gram per cubic centimeter. So that's why a gram per cubic centimeter would be a convenient unit for density. Something called specific gravity is a unitless quantity, and it is the ratio of a substance's density to the density of water. So if we have a density of any other liquid in grams per cubic centimeters, then we can divide that by 1 gram per cubic centimeter, so the units cancel out, and the specific gravity of that substance is basically its density, but without any units. So here, always make sure that you convert units from maybe kilograms per cubic meters to grams per cubic centimeters, or the other way around. Another term that we have to define is that of pressure. Pressure is force per unit area. The symbol for pressure is capital P, and the units, since pressure is force in newtons divided by area in square meters, then the units of pressure are newtons per meter squared. Another unit is the Pascal. So 1 Pascal is equivalent to 1 Newton per meter squared, and these are the SI units. Now, you may have encountered other units for pressure in chemistry, I believe. 1 atmosphere would be the preferred unit for pressure, but it's not the SI unit. So the conversion factor is 1 atmosphere is 1.013 times 10 to the 5th pascals, and it is also 760 millimeters of mercury, which is 760 torr. Torr is named after the physicist Torricelli, an Italian physicist who determined that a column that's 760 millimeters tall containing mercury exerts the same pressure on a fluid as does 1 atmosphere. So that's why we have all of these different units for pressure. Millimeters of mercury is often used in medicine. It's also used in weather reports. So if you're told that the air pressure is 766 millimeters of mercury, that means that there is a high pressure zone. So the pressure in the atmosphere is more than 1 atmosphere. So absolute pressure is the total pressure that is exerted on a body at a certain point, and absolute pressure is almost always a sum of different types of pressure. So to those different types of pressures can be the atmospheric pressure plus pressure from other objects that exert a force on the body. So if we have, for instance, a block submerged in a fluid, then the absolute pressure of that on that block will be the pressure of the fluid surrounding it, but that fluid has atmospheric pressure at the top. So the atmospheric pressure that's pressing on the fluid will press on the object inside the fluid as well. If we only look at the pressure inside a gauge, inside of a closed space, we call that the gauge pressure. So that means that we are taking away from the absolute pressure the atmospheric pressure. A very good example for this is the pressure in a tire. So when you're measuring the pressure in the tire, since there is the air in the tire is not in direct contact with the atmosphere, then inside the tire all of the pressure is gauge pressure. The atmosphere is on the outside, but it doesn't make contact at all with the air inside the tire. Let's look at some principles governing fluids at rest. So there's Pascal's principle that says that pressure applied to any part of an incompressible fluid will be transmitted throughout the fluid and to the walls of the vessel containing it. This principle is used a lot in hydraulic presses. It's used in like the dentist chair. When it gets lifted up, the dentist only has to exert a very small force to a little pedal that lifts the entire chair and the person in it a certain distance d. It is also used by mechanics when they lift the cars up on a ramp, not on a ramp, sorry. They lift the car up to work under the car. They again press on a pedal and the car gets lifted up by a piston, and that's also Pascal's principle. Archimedes' principle deals with buoyancy. So when a body is submerged in a fluid, then that body will experience an upward force from that fluid, and that upward force is called the buoyant force, and it is equal to the weight of the fluid displaced. So buoyant force is the weight of the fluid displaced, and then if we write weight as mass times g, then we write mass as density times volume, then the buoyant force will become density of the fluid times the volume that fluid was displaced times g, which is then the density of the fluid times the volume of the object, of the body that displaces the fluid. So that's the amount that the body is submerged in the fluid times g. We will look at examples of Pascal's principle and Archimedes' principle a little bit later. Another thing that is specific to fluids is that they experience two types of molecular forces. One is called cohesion, and that is the attractive force between molecules of the same liquid. So that's what keeps the liquid together. And a very good example for cohesion is liquid mercury. So if you've seen videos of mercury being spilled, you see how it likes to clump up and form these little round surfaces of mercury, and that's because of the cohesive forces between them. Then adhesion is an attractive force between the molecules of a liquid and some other substance. So an example for this is when you're drinking a delicious cup of tea and you want to drink the very last drop, you cannot, because some of the tea got stuck to the side of the cup. So that is the attractive force between the tea and the cup.